Welcome everyone. I'm excited to be here today to talk about our project supported by Science 6. My name is Isha Jadoon. In this presentation, we'll explore a digital twin for edge computing task offloading, focusing on a healthcare case study. We'll cover the key concepts, the methodology we used, and the insights we gained. Let's get started. Now, let's take a closer look at some of the key challenges we face with digital twins in healthcare. First, there's the issue of fair load distribution between the hospital and the edge devices. It's crucial to balance the processing workload so that neither side becomes a bottleneck, ensuring smooth and reliable operation. Next, we have the energy limits of wearables and edge servers. These devices need to operate efficiently within their power constraints, which can impact how much data they can process and transmit in real time. Then there's the challenge of latency, especially when it comes to critical alerts. Delays in processing vital signs or emergency signals can have serious consequences, so minimizing latency is essential for patient safety. All of these challenges highlight why digital twins truly need the edge. By processing data closer to where it's generated, we can address these issues directly, improving responsiveness, conserving energy, and maintaining a balanced load. This is fundamental to creating effective, real-time healthcare solutions that are both reliable and scalable. On this slide, I want to highlight how we utilize MILP-based scheduling to make smart decisions for each task. Essentially, the system evaluates whether a task should be executed locally, migrated to a different node, or dropped altogether, all while respecting the resource constraints of the network. This approach ensures we're making optimal choices in a complex environment. Our method focuses on jointly optimizing three critical factors: latency, energy consumption, and fairness across tasks. By doing so, we aim to improve overall system performance without sacrificing any particular aspect. Importantly, we also implement strategies to avoid dropping tasks whenever possible, which is vital in a hospital edge network where missing a task can have serious consequences. The ultimate goal here is to create a balanced, efficient scheduling framework that supports the real-time demands of a digital twin-enabled hospital environment. And the key contribution is that this comprehensive optimization approach helps manage resources effectively while maintaining high standards of service and fairness across all tasks. Let's take a closer look at the healthcare digital twin architecture. This slide outlines the key components that make up a comprehensive digital twin system in healthcare. First, you'll notice the central data layer, which is the foundation. It collects real-time data from various sources like wearable devices, electronic health records, and sensors embedded in medical equipment. This data is crucial because it feeds the entire system with up-to-date information. Next, we have the simulation and modeling layer. This is where advanced algorithms and machine learning models come into play, creating virtual replicas of patients or medical processes. These models help us predict health outcomes, test different treatment options, and understand complex physiological interactions without any risk to the patient. Then, there's the analytics and insights component. Here, the system analyzes all the incoming data and simulation results to generate actionable insights. This helps clinicians make more informed decisions, personalize treatments, and improve patient outcomes. Finally, we see the user interface or visualization layer. This is how healthcare providers interact with the digital twin, through dashboards, 3D visualizations, or other tools that make the complex data understandable and accessible. Connecting all of these points back to our overall theme, this architecture emphasizes how integrating real-time data, sophisticated modeling, and clear insights can revolutionize personalized medicine and proactive healthcare. It's about creating a seamless, intelligent system that supports better decision-making and ultimately enhances patient care. Now let's look at the overall system performance. First, while total energy consumption increases by about 26%, this is actually offset by a significant improvement in energy efficiency per successful task. Thanks to the balanced activation of all edge servers, each task consumes less energy overall. In fact, we see a 32% improvement over the traditional round-robin approach, reaching an energy efficiency score of 0.688. This indicates that our method makes better use of resources, reducing waste while maintaining high performance. Moving on to fairness, measured by Jane's index, our system scores 0.91. This is a notable achievement compared to 7.18% with round-robin and 45.9% with a hospital-only setup. It shows that our approach distributes workload more equitably across servers, ensuring no single server becomes overburdened. Regarding task drops, our system reduces dropped tasks by approximately 57% compared to round-robin and hospital-only methods. This means fewer tasks fail or are lost, contributing to a more reliable service. Finally, the average latency is around 130.8 milliseconds. Maintaining low latency is crucial for user experience, and these improvements demonstrate that our system balances efficiency, fairness, and responsiveness effectively. Overall, these system-level highlights reinforce how our approach optimizes performance across multiple dimensions, aligning with the broader goal of creating smarter, more reliable edge computing solutions. Thank you very much for your attention. If you have any questions or would like to discuss this further, please feel free to reach out to me at Aisha at UA, PT, or Cyan at A8, Edu, TR. Looking ahead, our future work will focus on integrating adaptive deep reinforcement learning techniques to approximate MILP solutions online, which will help us further optimize energy use in dynamic hospital environments. As we've seen, DT-driven MILP scheduling significantly enhances the reliability and responsiveness of healthcare edge systems, especially under realistic digital twin workloads. In conclusion, these approaches open new pathways for smart healthcare management, and our next steps will aim to refine these methods to better meet the challenges of real-world hospital operations. Thank you once again for your interest, and I look forward to connecting with you all soon.